Welcome to the Particle Physics Podcast. In today's episode, 7th October 2025, we're unpacking this year's Nobel Prize in Physics, awarded to John Clarke of UC Berkeley, Michel H. Devoret of Yale University, also affiliated with UCSB, and John M. Martinis of UCSB, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. A circuit that tunnels like a particle and absorbs energy in discrete steps? We'll explain how Josephson junctions make a many-electron system behave as a single quantum object, why that matters, and how these 1980s experiments laid the groundwork for today's superconducting qubits, circuit QQED, and quantum-limited amplifiers. We'll also sketch the scientific journeys of Clarke, Devoret, and Martinis, what they built, how they measured it at millikelvin temperatures, and how their ideas power modern quantum processors. Stick around for a clear, equation-light walkthrough of the physics, a quick timeline of milestones, and a look at what comes next for quantum technologies. I'm your host. Let's dive in. The 2025 Nobel Prize in Physics recognizes a decisive set of experiments that made the counterintuitive rules of the quantum world tangible in a device you could hold in your hand. In the mid-1980s, John Clarke, Michel H. Devoret, and John M. Martinis engineered and studied a superconducting electrical circuit in which two superconductors were separated by a thin, non-conducting layer, a Josephson-junction, and then showed, with careful biasing and exquisitely sensitive measurements, that this macroscopic, many-particle system behaves as a single quantum object. In one line of observation, the circuit escaped from a trapped, zero-voltage configuration, not by being thermally jolted over a barrier, but by tunneling through it, a hallmark of quantum mechanics. In a complementary line of observation, the same system absorbed and emitted energy only in discrete quanta, revealing a ladder of quantized levels rather than a smooth continuum. Together, these signatures, macroscopic quantum tunneling and energy quantization, establish that when dissipation is suppressed and the relevant degrees of freedom are engineered and controlled, quantum mechanics governs not only atoms and photons, but electrical circuits comprising vast numbers of Cooper pairs. This is the bridge the Nobel Committee celebrates in 2025. The leap from microscopic oddities to quantum properties on a human scale, with experiments performed in 1984 to 1985 that directly address the old question of how large a system can be and still show quantum behavior. In the committee's telling, that work has not only deepened our conceptual grasp of quantum mechanics, it has opened pathways toward the next generation of quantum technologies, including quantum computers, quantum sensors, and quantum cryptography, precisely because it proved that quantum effects can be stabilized, manipulated, and read out in engineered circuits. Official press release, popular information, and summary confirm the laureates, the exact citation, the on-a-chip held in the hand framing, the mid-1980s timing at Berkeley, the tunneling through a barrier analogy, and the discrete energy absorption-emission narrative, as well as the stated technological outlook. Within that collective achievement, the official materials also situate each laureate's personal arc and institutional home. John Clarke, born in Cambridge, UK, PhD, 1968, from the University of Cambridge, longtime professor at the University of California, Berkeley, stands in these documents as a central figure in superconducting device physics and measurement, who helped lead the 1984 to 1985 sequence of experiments, and whose Berkeley group provided the setting for showing that a macroscopic electrical degree of freedom can tunnel and display quantized levels. Michel H. Devoret, born in Paris, PhD, 1982, from Paris Sud University, professor at Yale University, New Haven, Connecticut, with an additional affiliation at the University of California, Santa Barbara, appears as a co-leader in that same experimental campaign, with the Nobel pages highlighting his role in demonstrating the two pillars, tunneling and quantization, that define the prize citation. John M. Martinis, Ph.D., 1987, from the University of California, Berkeley, professor at the University of California, Santa Barbara, is presented as the third member of the trio who, together with Clarke and Devoret, executed the Berkeley-based studies that pushed electrical circuits into an unambiguous quantum regime. While the press release and popular summary are brief by design, they provide the canonical identities, affiliations, and the core scientific contribution of each laureate in the shared discovery. They explicitly list the institutions, Berkeley, Yale, UCSB, the roles of the superconducting circuit and Josephson-junction, and the twin signatures that grounded the committee's decision. As a public marker of the announcement, the Nobel channels also amplified the decision on social media, broadcasting the exact citation and the three names as part of the same, coordinated reveal of the award. All biographical points, institutional affiliations, and the formal wording of the discovery are taken from the Nobel pages. The social post echoes the same names and citations. Scientifically, the Nobel narrative frames the discovery with two complementary images: a tilted energy landscape in which a macroscopic degree of freedom can either hop over a barrier by thermal activation or pass through it by quantum tunneling, and a quantized spectrum in which the same system engages with electromagnetic fields only at specific energies, absorbing or emitting in doses of specific sizes. The laureates' experiments used a superconducting junction so that the collective phase of the condensate becomes the relevant quantum coordinate. By refining the circuit parameters and the measurement, they revealed I, a temperature-insensitive escape channel at low temperature that signals tunneling from a metastable zero-voltage state, and 2, discrete transitions that betray quantized levels inside the effective potential. The upshot is conceptual and practical at once. If a many-body circuit can maintain a coherent, controllable quantum variable, then it becomes a natural substrate for engineered quantum systems, the very premise of later circuit-based quantum information platforms. The Nobel materials make this connection explicit, noting that quantum mechanics underlies today's digital technologies and that the laureates' electrical circuit experiments helped carve the path toward quantum computers, sensors, and cryptographic devices. In short, by demonstrating that macroscopic tunneling and energy quantization are not confined to microscopic particles, but can arise in carefully built circuits, Clarke, Devoret, and Martinis supplied both a conceptual proof and a technological template. Quantum behavior can be stabilized, addressed, and read out in hardware we design, a message that continues to shape how researchers imagine, build, and scale quantum devices. All descriptions of tunneling through a wall, quantized energy exchange, the macroscopic versus microscopic contrast, and the explicit technology outlook are paraphrased from the Nobel press release and popular information pages.